Hi and welcome to the 8th part of this advanced C# course. In this video, we'll focus on the use of attributes in C#. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future content. If you like this video at any point, please consider giving it a thumbs up. It will be greatly appreciated. So, let's discuss attributes. Attributes allow the developer to add metadata in a declarative way to program elements in code, for example, classes, methods, properties, parameters, etc. A declared attribute is instantiated into an object at runtime, and at compile time, we can declare attributes against program elements to provide additional metadata to relevant program elements. The developer is also able to declare global attributes against assemblies, and in doing so add or modify metadata about the relevant assembly. So, the developer can use attributes to add or modify metadata about a particular program element or the assembly itself. In this video, we'll also briefly look at reflection. Reflection is a technology that we can use to read the metadata provided through the use of attributes at runtime. We are then able to, for example, implement code logic based on the metadata provided through the use of attributes. We'll look at how we can do this later in this video. There are two broad categories for attributes: predefined attributes and custom attributes. Predefined attributes are built into the base class libraries in .NET. In this video, we'll look at two main types of predefined attributes: global predefined attributes and general predefined attributes. Global attributes, like for example assembly version attribute and assembly description attribute, facilitate adding and modifying metadata for an assembly. General attributes, like for example conditional attribute, obsolete attribute, and attribute usage, can be applied to appropriate program elements. We'll start by implementing a code example using the assembly version attribute and assembly description attribute, which are global attributes. We'll use reflection to read the relevant assembly metadata and output the assembly metadata to the console screen. We'll then implement a code example using the following general attributes: conditional attribute, obsolete attribute, and attribute usage. The attribute usage attribute will be declared on our own custom attributes that we'll create a bit later in this video. We'll use custom attributes and reflection to implement field validation functionality. We'll demonstrate how custom attributes can be created by creating classes that inherit from the built-in system.attribute class. Later in this video, we are going to create custom attributes as part of validation logic that imitates how the ASP .NET MVC framework provides flexibility to developers through the use of reusable validation-related attributes. Right, let's create our code examples so that we can gain an understanding of attributes in C#. Let's create a .NET Core console application project. Let's name this project Attributes Examples. Let's ensure that we are using .NET 5 for this project. If you haven't yet installed .NET 5, please see a link below in the description where you are able to download the .NET 5 SDK. Note that you'll mostly be able to follow along even using earlier versions of .NET, but it is advisable to download .NET 5 to follow along with this tutorial and future tutorials. One of my core aims is to keep these tutorials right up to date. Please view a video created for this channel about the significance of the release of .NET 5. A link to this video can be found below in the description. So let's say that we wish to declare the assembly version global attribute in our code. We are able to do this by declaring this global attribute between the namespace declaration and the using directives. Okay, so why can't I see the assembly version attribute in the IntelliSense dropdown? The reason is that the assembly version attribute is part of the system.reflection namespace. So let's add a using directive to the system.reflection namespace. And now we are able to see the assembly version attribute along with other global attributes in the IntelliSense dropdown list. And we can now declare the global attribute against our assembly like this. So here we are attempting to set our attribute version number to 2.0.1 through the declaration of the assembly version global attribute. Great, so let's see what happens when we attempt to compile the code. So we have a compile time error. Let's look at our error list to take a look at the details of this error. The description of the error is duplicate system.reflection.assembly version attribute. So let's double-click on the error item in our list that is causing the compile time error to occur. Okay, so a new file is open and we can see a red squiggly line under the offending code. It is a file that has a name that contains the assembly name followed by the suffix .assembly info, and we are able to find this file within our project's directory structure. And if we look at the comments within this file, it is clear that this file has been auto-generated. It's in fact been auto-generated by MS Build. Let's navigate to this URL to read a bit about MS Build. The Microsoft Build engine is a platform for building applications. This engine, which is also known as MS Build, provides an XML schema for a project file that controls how the build platform processes and builds software. Visual Studio uses MS Build, but MS Build doesn't depend on Visual Studio. By invoking msbuild.exe on your project or solution file, you can orchestrate and build products in environments where Visual Studio isn't installed. Visual Studio uses MS Build to load and build managed projects. The project files in Visual Studio .csproj, .vbproj, .vcxproj, and others contain MS Build XML code that executes when you build a project by using the IDE. Visual Studio projects import all the necessary settings and build processes to do typical development work. But you can extend or modify them from within Visual Studio or by using an XML editor. So the basic point I'm trying to make here is that many of these global attributes will be automatically declared in the assembly info file when compiling your code using the Visual Studio IDE. You can gain access to some of these global attributes through the Visual Studio IDE. If you try to declare a global attribute, as I have attempted to here, you may get a compile time error because MS Build has automatically declared the global attribute in the assembly info file. As we have seen, this results in a duplication of the relevant global attribute declaration, which ultimately results in a compile time error occurring. You are able to declare certain global attributes in the way we tried to declare the assembly version attribute. For example, let's declare the assembly description attribute. Let's comment out the assembly version attribute declaration. Let's add our own assembly description metadata to our assembly through a declaration of the assembly description global attribute. Let's pass a value of my assembly description to the constructor of the assembly description attribute. Note that depending on how the relevant attribute has been written, when the developer declares an attribute, the developer is able to provide custom metadata to the relevant attribute through the attribute's exposed public properties or the relevant attribute's constructor parameters. So, we know that the purpose of attributes is so that we can add or modify metadata against certain program elements or even against the assembly itself. Note that attributes on their own do not change application behavior. The metadata provided through attribute declarations can be read at runtime through the use of reflection. Relevant metadata can then be evaluated by our code, and appropriate code logic can be invoked based on the declared metadata. So this is how the Microsoft Docs describes reflection. Reflection provides objects of type that describe assemblies, modules, and types. You can use reflection to dynamically create an instance of a type, bind the types to an existing object, or get the type from an existing object and invoke its methods or access its fields and properties. If you're using attributes in your code, reflection enables you to access them. Right, so let's use reflection to access and read certain metadata that has been added through the use of global attributes. So we need a using directive to the system.reflection namespace, which has already been included in our code. So let's write some code in our main method. Let's get a reference to the current assembly. We can do this by getting a reference to the program class's type and then assigning its assembly property value to a variable. We have named our variable this asm, referring to the current assembly. We can then get the relevant assembly name by using the assembly reference stored in the thisAssemb variable and calling its getName method. And we can access the assembly's version information through the version property. Now we want to read the assembly's description, which should be the description that we included when we declared the assembly description global attribute. To get a reference to the assembly description attribute, we can call the getCustomAttributes method on the thisAssemb object and pass in the type of the attribute of interest to us. Note that we are using the typeOf method to get a reference to the object type of the relevant attribute. Remember, attributes in C# are objects at runtime. An object instantiated from the assembly description attribute class should be the first item in our object array. We can use the as operator to cast the object to the assembly description attribute type. If the casting operation fails, null will be returned. If the operation succeeds, an object of the assembly description attribute type is returned. Let's write code to write out the metadata information about the current assembly that we have been able to retrieve through reflection to the console screen. Let's run the code. Great! So we have looked at examples of global predefined attributes. Let's look at some general predefined attributes. Let's start with the conditional attribute. Let's first add a new standard library project to our solution. And let's name our project logging component. Let's remove the automatically created class named class1 and add a new class named logging to our new project. Let's add a public static method to the logging class named logToScreen. It contains one parameter named MSG and is defined as a string. The code for this method simply outputs the value referenced by the MSG argument to the console screen. Let's declare the conditional attribute against the logToScreen program element. We have a red squiggly line because the conditional attribute is a member of the system.diagnostics namespace. So let's add a using directive to the system.diagnostics namespace. And now let's pass in an argument into the constructor of our conditional attribute. Let's pass in the text log_info. So what does log_info mean? Log_info is a piece of text that I've made up. This text represents a symbol in our code. We can use the define preprocessor directive and include the log_info symbol in our code. If the log_info symbol is defined using the preprocessor define directive within a file containing method calls to the logToScreen method, the code within the logToScreen method will be executed at runtime. However, if the predefined processor directive is not used to define the log_info symbol in the file where the logToScreen method is called, its code will not be executed at runtime because we have used the conditional attribute to declare to the compiler that we would like this behavior to occur regarding the logToScreen program element. So, the combination of the conditional attribute and the use of the define preprocessor directive can act like a switching mechanism, i.e. using this mechanism we are able to switch certain code on or off. This is especially useful for debugging purposes. If this is not clear, don't worry. We will demonstrate what is meant here through a code example. We are able to define our log_info symbol through the use of a preprocessor directive. We are going to use the define preprocessor directive for this purpose. Preprocessor identifiers are used to help in conditional compilation. If we navigate to this URL, we can see some of the preprocessor directives available in C#. For more information on preprocessor directives, please use this section of the Microsoft Docs as your guide. So here we have the hash define preprocessor directive that we can use to define a symbol in our code. So let's see how we can use a particular preprocessor directive in conjunction with the conditional attribute to conditionally output information to the console screen through our log_to_screen method. We must add our appropriate preprocessor directive code right at the top of our program.cs file in our code editors like this to implement the desired functionality. You can see we have the define preprocessor identifier in this line of code, as well as the log_info symbol that we made up and passed as text to our conditional attribute, which was declared against the log_to_screen program element. Let's include a using directive to our logging component namespace. In our main method, let's make a call to the logging.log_to_screen method and pass in the following text as an argument to the MSG parameter. This code is testing logging functionality. Let's run the code. And as expected, the appropriate text is written to the console screen. So now let's see what happens when we comment out the relevant preprocessor directive code and run the code again. And you can see that nothing has been outputted to the console screen. Using our preprocessor directive, we can switch the execution of the code against which the relevant conditional attribute is applied on and off at compile time. This functionality can be very useful for debugging purposes. So let's say we have a change to our logging component where we want all logging to be done to a text file rather than to the console screen, and we want the consumers of our code to use the method that logs the information to a text file rather than to the console screen. So how can we let the consumers know to use the log_to_file method rather than the log_to_screen method? We can simply declare the obsolete predefined general attribute against the log_to_screen method. Let's create a public static method named log_to_file. In the interests of time, rather than writing the code to actually log the value passed into this method to a file, let's just write code to output the value to the console screen and pretend that its method logs relevant text to a text file. Okay, so let's declare the obsolete attribute against the log_to_screen method. And let's pass a meaningful message to the constructor of the obsolete attribute. So we want any calling code that is currently using the log_to_screen method to receive the following warning message. The log_to_screen method has now been deprecated. Please use the log_to_file method instead. So now if we go to our main method, we can immediately see a green squiggly line under the code that is calling the log_to_screen method. And if we hover our mouse pointers over the green squiggly line, we can see that the text that we passed as an argument to the obsolete attribute is presented to us. And note that if we want to force the user of our code to not use the log_to_screen method at all, we can set a second parameter in the obsolete attribute to true. If this value is set to true, an error is flagged when a user attempts to use the deprecated method, i.e. the log_to_screen method. Now you can see that the green squiggly line has turned into a red squiggly line, meaning that we no longer just receive a warning message. We are receiving an error message. This means we won't be able to compile the code. The last predefined attribute that I wish to discuss is the attribute usage attribute. We are going to create our own custom attributes and use reflection to read the relevant metadata added to relevant program elements through our custom attributes. So reflection and attributes will be implemented to provide flexibility to developers using our custom attributes to declare how relevant fields should be validated. This code is going to be very similar to the code that the ASP.NET MVC framework implements for field validation. In ASP.NET MVC, we can declare certain validation-related attributes against relevant program elements, and the MVC framework automatically handles validation of relevant fields for us behind the scenes, as it were. In this code example, however, we are going to create the custom attributes used for declaring how we want relevant fields validated, and we will also write code using reflection to read the attribute data declared against relevant program elements. In this case, the program elements will be properties. We will also write the validation code related to each of our custom attributes. Okay, so let's add a new standard library project to our solution. Let's name this project Validation Component. Let's delete the class that was automatically created by Visual Studio. Let's create a new folder named Custom Attributes. Let's add our first custom attribute class to the Custom Attributes folder. Let's right-click the Custom Attributes folder and add a new class. Let's name this class Required Attribute. Note that we must include the attribute suffix in the class name of our custom attribute. However, when we declare our custom attribute, you'll see that in the declaration we can omit the attribute suffix from the attribute name. We are, however, allowed to include the attribute suffix in our attribute declaration, but functionally this is unnecessary. We'll demonstrate this a bit later. The code for this attribute is very simple. Let's create a public auto-implemented property of type string named errorMessage. Let's add code to a parameterless constructor whereby the errorMessage property is set to a default value. So let's say we want a default error message of you cannot leave field, and then in curly brackets we have a 0 followed by the word empty. So the 0 in curly brackets allows the relevant field name to be inserted into the message at a later time. This is achieved through the use of composite formatting. If you are not familiar with composite formatting regarding string values, please view a tutorial created for this channel on C# strings. A link to this tutorial has been provided below in the description. Right, let's create a parameterized constructor. This will allow the developer to pass in a custom error message when declaring the required attribute against the relevant program element. The declaration of the required attribute will be demonstrated a bit later. In order for our class to be recognized as a custom attribute, we must ensure that our class inherits from the built-in system.attribute class. A custom attribute must inherit from the system.attribute class either directly, as we are doing here, or indirectly. For example, if our class inherited from another user-defined class that inherits from the system.attribute built-in class. So now all that is left to do is apply the predefined attribute usage attribute against our required attribute class. Like with the obsolete predefined attribute, the attribute usage predefined attribute is a member of the system namespace. Basically, the attribute usage predefined attribute allows us to provide metadata to the compiler. That will tell the compiler which elements are allowed to have our predefined attribute declared against them. So we can apply rules or constraints through the use of the attribute usage predefined attribute against our custom attribute at the class level. This is an example of declaring an attribute against a class. So in the first argument passed into the attribute usage attribute, we can declare which program elements are allowed to be decorated with our custom attribute. So if we have decided that we only want our custom attribute to be declared on the following program elements, fields, parameters, and properties, we can declare this by passing in this code to the first parameter of the attribute usage attributes constructor like this. So here we are declaring which target program elements are able to be decorated with our required custom attribute. We can optionally set a property of type Boolean named allowMultiple through our declaration. If we set the allowMultiple property to true, this means multiple instances of our custom attribute can be declared against a single program element. We only want one instance of our custom attribute to be declared against a single program element, so let's set the allowMultiple property to false. We also have a property named inherited that we can optionally set through this declaration. Setting this property determines whether the relevant custom attribute is inherited by a derived class. In this example, we won't set this property. And that's it. We have now created our required custom attribute. So let's create our next custom attribute. Let's add a new class file to our custom attributes folder, and let's name this class string length attribute. Let's add 3 public auto-implemented properties to our string length attribute class. Max length, for the storage of an integer value denoting the maximum number of characters that a user can enter for a field related to a property against which the string length attribute has been declared. Error message, for the storage of a string value denoting the message outputted to the user when the user has entered an invalid value into a field related to a property against which the string length attribute has been declared. Min length, for the storage of an integer value denoting the minimum number of characters that a user can enter for a field related to a property against which the string length attribute has been declared. So let's create a private method named setProperties that we can reuse for setting our public properties. This method will be called from a number of constructor overloads that we'll implement in a bit for this class. This method does not return a value and contains 3 parameters that correlate to the public properties that we have already created. The first parameter is max length, which is defined as int. The second parameter is error message, defined as string. The third parameter is min length, defined as a nullable integer. The question mark symbol following the int keyword denotes that this parameter is nullable. So, it is a nullable value type parameter, because it's defined as an integer, which is of course a value type. Let's also make our min length parameter optional. We can do this in C# by simply assigning the relevant parameter a default value within the method definition like this. So if a value is not passed into this parameter, by default the min length argument will have a value of null. Before we move on with our example, let's go to the Microsoft Docs, specifically to this location, to read a bit about nullable value types. A nullable value type T ? Represents all values of its underlying value type T and an addition of null value. For example, you can assign any of the following 3 values to a bool ? variable: true, false, or null. An underlying value type T cannot be a nullable value type itself. Very basically, a null value means that a value for the relevant variable has not been set. Adding a question mark at the end of the value type definition for a variable or a parameter means we have the option of storing a null value in the relevant variable or parameter. Note that optional parameters must be included at the end of the parameter list in the relevant method's method signature. Okay, so let's implement the logic for the setProperties private method. So firstly, let's check to see if the error message argument contains an empty string. If it does, we want to set a default error message value. In order for our error message to contain appropriate text, depending on whether the min-length value is set, we can create a nested if statement. So if the min-length value is null, let's appropriately set our default error message. If the min-length value is not null, let's include appropriate text relating to the min-length value within our default error message. So if the developer does not pass in an error message when declaring the string length attribute against an appropriate program element, a default error message will be used. For the scenario where an error message value is set when the relevant attribute is declared against a program element, the error message provided must be assigned to the error message public property of the attribute. Then let's set the max length property. This is a property value that the developer must pass in when declaring the string length attribute against an appropriate program element. Let's then assign the appropriate value to the min-length property. So let's use a ternary operator to check if the min-length argument is null, i.e. has not been set by the developer declaring the string length attribute against an appropriate program element. If the min-length argument is null, let's assign 0 to the min-length property. If the min-length argument contains a value, let's assign the value to the min-length property. So let's create our constructor overloads. Firstly, let's create a constructor that contains just the max length parameter. Then within our constructor, let's call our private setProperties method to assign values to the appropriate public properties of the string length attribute class. Okay, I also want to make the error message parameter in the setProperties method an optional parameter. We can do this by simply assigning default value to the error message parameter like this. Note that the parameter after the error message parameter in our parameter list is also the last parameter in the parameter list and is optional. So it is perfectly legal to make our error message parameter optional. Remember, the optional parameters must be included at the end of the relevant parameter list. Let's create a constructor overload that contains the max length parameter and the error message parameter. Then let's use our private setProperties method to assign values to the appropriate public properties of the string length attribute class. Let's create a constructor overload that contains the max length parameter and the min length parameter. Let's use our private setProperties method to assign values to the appropriate public properties of the string length attribute class. Note how we are passing in a value to the min-length optional parameter of the setProperties method. We need to be specific as to what parameter is being passed an argument here, because in this case, we are not passing in an argument to the error message parameter. The fact that the error message parameter and the min-length parameter are both optional means in cases like this, we have to make it clear which parameter we want to pass our argument to. Let's create one more constructor overload. This constructor overload contains the max length parameter, the error message parameter, and the min length parameter. Let's use our private setProperties method one more time to assign values to the appropriate public properties of the string length attribute class. Let's ensure that we include the code whereby our class inherits from the system.attribute built-in class. So now let's declare the attribute usage predefined attribute against our string length attribute class. So we can copy the attribute usage declaration from our required attribute class and appropriately paste it in to declare the attribute usage attribute against our string length attribute class. Great, so we have now completed two custom attributes, the required attribute custom attribute and the string length custom attribute. Let's create one more custom attribute. This attribute will be responsible for indicating, when declared against a program element, that the input field's value related to the relevant program element should match a specified regular expression pattern. So regular expressions are great for defining patterns that an input field value must match for field types that must be constrained to a particular format, like, for example, postcodes, phone numbers, credit card numbers, email addresses, etc. So the validation code for fields like this will be simple. If the relevant input field value matches the specified regular expression pattern, the user's input is deemed as valid. If, however, the input field value does not match the specified regular expression pattern, the user's input is deemed as invalid. We can implement the validation logic related to our custom attributes once we have completed the code for this final custom attribute. So let's add a class to our custom attributes folder and let's name this class regular expression attribute. Let's create two public auto-implemented properties. The first property, named errorMessage, is of the string date type. The second property, named pattern, is also of the string date type. The pattern property denotes the regular expression pattern that must be supplied by the developer when the regular expression custom attribute is declared against an appropriate program element. Let's create two constructor overloads. The first constructor overload contains one parameter named pattern. The developer is able to pass an appropriate regular expression pattern argument to this parameter when declaring the regular expression custom attribute against an appropriate program element. The error message argument is not passed into this constructor, but we can provide a default error message in this constructor and assign it to the error message property. Let's create a constructor overload. This constructor contains two parameters, one denoting the regular expression pattern and the other denoting the error message. So this constructor allows the developer to pass in a regular expression pattern argument, as well as a custom error message to a declaration when declaring this attribute against a program element. So all we need to do within the constructor is assign the public property members of this class with the appropriate values passed into the relevant constructor as arguments. Let's ensure that we include the code whereby our class inherits from the system.attribute built-in class. The last step is to appropriately declare the attribute usage predefined attribute against the regular expression attribute class. This declaration will be the same declaration applied against our other two custom attribute classes. So let's copy the appropriate declaration from one of our other custom attribute classes and appropriately paste the contents of our clipboards into our regular expression attribute class file. So now we have created three custom attributes implemented in three separate files. The first custom attribute we created is named required attribute. When this attribute is declared against an appropriate program element, this means that the associated input field must not be left empty. If it is left empty, the field value is deemed as invalid. The second custom attribute we created is named string length attribute. When this attribute is declared against an appropriate program element, this means the associated input field must contain a character length that falls within the boundaries defined by a specified minimum value and a specified maximum value. The third custom attribute we created is named regular expression attribute. When this attribute is declared against an appropriate program element, this means that the associated input field must contain a value that matches a specified regular expression pattern. So through the declaration of one or more of our custom attributes, a developer can express how a certain input field should be validated. Without the logic to implement the validation rules, however, these attributes are useless. These custom attributes perform no functionality other than to add metadata to relevant program elements. So the next step is to write the validation code. We must write the validation logic that correlates with each of our custom attributes. Through the use of reflection, we'll be able to read the metadata added to the relevant program elements through the use of our custom attributes. The use of our custom attributes is for the purpose of declaring how validation logic is related with relevant program elements, which are also related to relevant input fields. So let's write the relevant validation logic. So to do this, let's first add a new class named validation directly to the project node. So we want this class to be separate from our custom attribute classes. We are going to implement our own validation code in this class. So we first want to create the validation logic that corresponds to each of our custom attributes: the required attribute, the string length attribute, and the regular expression attribute. Let's encapsulate this functionality within 3 private methods. Let's first implement the validation logic that corresponds to the required attribute. So let's create a private static method named fieldRequiredIsValid that returns a Boolean value. This method contains one parameter. Let's name this parameter enteredValue and define it as a string. The logic for this method is basic. If the entered value passed into this method as an argument is not null or empty, return true, because this means the user has entered a value, which makes the input field entry valid. If the code that returns true is not executed, this means the entered value is invalid and false must be returned to the calling code. Let's implement the validation logic that corresponds to the string length attribute. The method signature for this method is the same as the fieldRequiredIsValid method, except we need to also pass in a field of type string length attribute to this method, in addition to the parameter representing the entered value. This is so that we can access the min length and max length public properties that we implemented for the string length attribute class. The values stored in these 2 properties are integral to the validation logic performed against relevant inputted values. Let's name this method fieldStringLengthIsValid. So to implement the validation code, let's implement an if statement where the condition evaluates the entered value argument to see if its character length is greater than or equal to the min length property and is less than or equal to the max length property. If the character length of the entered value argument falls within the range defined by the min length and max length property values, the entered value is valid, so we can return true to the calling code. If, however, the character length of the entered value does not fall within the specified range, we must return false because the entered value is not valid. So let's now implement the validation private method that corresponds to the regular expression attribute. So the method signature is almost the same as the fieldStringLengthIsValid method's method signature. Let's appropriately name this method fieldPatternMatchIsValid. Instead of including a parameter of type string-length attribute, let's include a parameter of type regular expression attribute. This is so that we can access the public property named pattern, which is a member of the regular expression attribute class. The pattern property will contain the regular expression pattern against which we need to validate the entered value. So let's use the regex class to perform our validation logic. This class is a member of the system.text.regularExpressions namespace, so let's include an appropriate using directive. The regex class contains a public static method named is match. We can use this method to validate the entered value against the relevant regular expression pattern. If the isMatch method returns true, this means the entered value is valid, so we must return true to the calling code. If, however, the isMatch method returns false, this means the entered value is not valid and we must return false to the calling code. Okay, so we have now implemented the validation logic that corresponds to our custom attributes. Let's create a public static method named propertyValueIsValid that returns a Boolean value. This method is responsible for calling relevant validation code that is relevant to a specific program element and a user inputted value. The validation code executed is determined by the custom attributes that have been declared against the relevant program element. In the interests of keeping this code simple, the code will only be relevant to a program element that is a property. So the first item in the parameter list for the propertyValueIsValid method is a parameter of type type. This parameter represents the type that contains properties against which our custom attributes may have been declared. For example, a user-defined type representing an employee record. The next parameter represents the value that a user enters, i.e., an input field, which is correlated to a particular property and needs to be validated by our code. This parameter is appropriately named entered value. The next parameter represents the program element, which will be a property in this case, that is a member of the type represented in the first parameter. So, for example, the program element could be the first name property, which is a member of a user-defined type named employee. The last parameter for this method represents the error message that will be displayed to the user if the user's input is deemed as invalid. We want to output the error message value, so let's include the out keyword in the relevant parameter definition. Let's implement the logic for this method. Firstly, let's get a reference to the relevant program element. So the program element in this example will be the property on which one or more of our custom attributes has been declared. So, for example, if we are validating the first name property on the employee user-defined type, the element name argument will contain the literal text first name, which is the name of the first name property. To get a reference to the user-defined type, in this case employee, the calling code would pass in type of employee. This means we can use reflection to inspect the relevant program element to ascertain which custom attributes have been declared against the relevant program element. Using reflection, we can then ascertain how we should validate the relevant entered value. So let's write code to get a reference to the relevant program element, which in this case will be a property. Reflection can be used to get relevant information about a program element. We want to know in our code what custom attributes have been declared against the relevant program element. So we can use the property info type, which is a member of the system.reflection namespace, to gain access to the property information that we need. We must include a using directive to the system.reflection namespace. Let's define a variable named prop as the property info type, and let's assign a value returned from a call to a method named getProperty, which is invoked on the type argument passed into the t parameter of this method. Note that we need to pass the element name argument to the getProperty method. The element name argument will store a reference to the name of the relevant property. We now have a reference to the relevant property information. We can use the getCustomAttributes method to return a collection of custom attributes that have been declared against the relevant property. We can assign the returned value to an array of type attribute. The getCustomAttributes method is returning a collection of type IEnumerable, and I want to store a reference to the relevant custom attribute objects in an array, so let's use links to array extension method to convert the IEnumerable collection into an array. let's initialize the error message output parameter to an empty string. Let's write code to perform a for each loop and loop through each attribute object declared against the relevant program element. Then within the for each loop, let's implement a switch statement and use pattern matching code to get a reference to the relevant custom attribute objects so that we can perform appropriate validation on the entered value. So the switch statement evaluates the type of each relevant attribute object using pattern matching. Using pattern matching, we are able to get a reference to the attribute objects that have been declared against the relevant program element. This is the magic of pattern matching in action. Pattern matching was introduced in C# version 7. It allows the developer to write code to assess whether an object type matches the object type specified in a case statement. If there is a match, a reference to the relevant object is made available on the same line of the code as the case statement. So here we have case required attribute. If the object referenced by the attr variable is of type required attribute, the RA variable is assigned the value referenced by the attr variable. We are then able to use the RA variable in our validation code that resides within the relevant case block. So we can call the appropriate private method for validating required fields that we implemented earlier to validate the relevant user entered value. If the entered value is deemed as invalid, we can output an error message to the user through the error message output parameter, which has been appropriately marked with the out keyword, meaning we can output a value through this parameter to calling client code. If the relevant user input fails validation, we need the property value is valid method to return false. So let's include the other case statements pertaining to the other two custom attributes. So let's implement the case block for the string length custom attribute. And lastly, let's implement the case block for the regular expression custom attribute. Great. Let's write the calling client code. Let's go to the .NET Core Console project. Let's start by creating classes that can represent data models. The first model will be a class that represents an employee record. So let's create a new folder and name it Models. Let's add a new class named Employee to the Models folder. This class contains 6 auto-implemented properties: ID as int, first name as string, last name as string, phone number as string, email address as string, and postcode as string. Great. So we are now going to appropriately declare our custom attributes against the properties we have just added to the employee class. These attribute declarations will indicate to our validation code how the input values associated with the employee class's relevant properties should be validated. Let's include an appropriate using directive at the top of our code to the validation component.customattributes namespace. So let's apply the required attribute to the ID program element. Notice how when we declare our custom attributes, we don't need to include the attribute suffix. So even though the class representing the required attribute is named required attribute, when we declare the attribute against the relevant program element, we can omit the attribute suffix. So in this case, we can declare the attribute using the name required. Let's declare the string length attribute against the first name property. Let's pass appropriate values to the constructor of the string length attribute. So let's say the maximum character length for the first name input field should be 15. Our next argument is the error message we wish to output to the user if the user enters an invalid value for the first name field. For the last parameter, let's say the user must enter a value for the first name field that has at least 2 characters. Let's declare the required attribute against the first name property. So we can copy and paste the custom attributes declared against the first name property to the last name property. Now the phone number property will include the same attributes and settings applied against the first name and last name properties. But we also want to validate the phone number against a regular expression pattern that can be used to validate UK phone numbers. So let's navigate to this URL. I find this website very useful for finding regular expression patterns. Let's do a search for UK phone numbers. Let's copy an appropriate pattern from our search results. We can then appropriately pass this pattern as an argument to our regular expression custom attribute. So let's appropriately paste our pattern into our code. Note that we may need to include the @ symbol preceding the string references of the regular expression patterns. This is because the pattern may include / characters which need to be escaped because the / character is used by C# within strings for escape sequences. For example, the \n escape sequence denotes a new line within a string. The \t escape sequence denotes a horizontal tab character within a string, etc. So by including the @ symbol preceding the string, we are indicating that any / character should be interpreted as a literal / character and not as part of an escape sequence. So let's apply the custom attributes for the email address property. Let's find an appropriate regular expression pattern and appropriately paste it into our code. Let's do the same for the postcode address. Let's say we need the postcode to be a valid UK postcode. Great. So now let's build a basic front end so that we can test our validation code. Let's write a reusable private method that contains logic to prompt the user for a relevant field value. We need this code to run within an infinite loop, which we can implement using a do loop. Once the user enters a valid value, the code will break out of the infinite loop. The getInput method returns true once the user has inputted valid data for the relevant input field. We can use the out keyword to make the last field an output parameter where we can pass the valid data to the calling code. Let's go to the main method and implement the calling code. Let's instantiate an object of type employee. Let's ensure that we have a using directive to the attributes examples.models namespace. Because of course the employee class is a member of this namespace. Let's create 3 local string variables, empid, first name, and postcode. We need to get a reference to the employee class's type. We can do this using the typeof method, like this. Let's write code to handle the user input for the employee's ID. So once the user has entered a valid value for this field, the valid data can be assigned to the ID property. The ID property of the employee type is an integer value. So let's write code to convert the relevant string value to an integer value. Let's write code to handle the user input for the employee's first name field. Once the user has entered a valid value for this field, the inputted value can be assigned to the first name property. Let's write code to handle the user input for the employee's postcode. So let's write code so that once the user has entered valid information for the relevant fields, a message stating that the user has now entered valid data for the relevant employee is outputted to the console screen. Great, let's test the code. So if we press the Enter key without entering an employee ID, we get an expected output. An appropriate error message is outputted to the console screen. Let's enter a valid ID. Great. So if we leave the first name field blank and press the Enter key, we get an appropriate error message outputted to the console screen. If we enter just one character for the first name field, the string length validation code deems our input as invalid and an appropriate error message is output to the console screen. So now if we enter a value for our first name field that contains a character length that falls within the character length range, which is between 2 and 15, this input is deemed as valid. If we leave the postcode field blank, we are presented with an appropriate error message. Let's enter a valid UK postcode. Great. Just to demonstrate that we are able to reuse our custom attributes on other user-defined types, let's create another model. Let's create a class to represent a department record. Let's apply some of our custom attributes. Let's go to our main method and test our code. In the interests of time, we'll only include the department short name field in our test here. Excellent. So let's use a predefined attribute that already exists in a .NET library. So the attribute I want to use is named JSON_ignore. So we want to add functionality to output our employee object to the console screen in JSON format. Using the JSON_ignore attribute, we can choose which fields to exclude from our employee object JSON output. Let's declare the JSON_ignore attribute against the phone number property and the postcode property. Let's go to our main method and write the code to serialize the employee object in JSON format. Let's run the code. And you can see that the JSON output does not include the phone number and the postcode fields. Great. Let's comment out the JSON_ignore attribute declarations so that we can include all of our property values for the relevant employee object in our JSON formatted output. Okay, so I accidentally inputted Bob's surname, which is Jones, for the postcode field, and I've noticed that there is a bug in our code. The error message format outputted to the screen is incorrect. The validation was run correctly, i.e. clearly Jones is not a valid postcode, but the error message itself is incorrect. The 0 wrapped in curly brackets in the appropriate code should serve as a placeholder for the property name of the property against which the relevant attribute has been declared. The 1 wrapped in curly brackets should serve as a placeholder for the regular expression pattern specified for the purpose of validating that a postcode entered by the user is in a correct UK postcode format. So I can see what is causing this issue. We need to remove the dollar symbol preceding the error message specified in this constructor. We want to use composite string formatting and not string interpolation for this string value. For details on composite formatting versus string interpolation, please view a video on C# strings created by this channel. A link to this tutorial is available below in the description. So let's repeat the input that we specified in the previous test. Great, the validation code is correct, and the outputted error message is also correct. Okay, but in our outputted JSON text here, the postcode field is null. So, it looks like we have another bug here. Oh right, so when I copied and pasted the code here, I forgot to change the relevant code so that the postcode property is set to the user's input. Okay, let's correct this. And let's test the code again. Excellent. We looked at how attributes are used in code to add metadata to program elements like classes, methods, properties, etc. And reflection can be used to read the metadata added through the use of the attributes at runtime. We discussed that there are two broad categories in C# for attributes, namely predefined attributes, which are built into the .NET base class libraries, and custom attributes, which allow the developer to implement the developer's own attributes by creating a class that inherits from the system.attribute built-in class, either directly or indirectly. We created code examples using predefined global attributes, namely assembly version attribute and assembly description attribute. This demonstrated how global attributes can be used to add and modify metadata at the assembly scope. We created code examples using predefined general attributes, namely conditional attribute, obsolete attribute, and attribute usage attribute. This demonstrated how we can add and modify metadata for program elements. We then created our own custom attributes as part of code logic used for the purpose of field validation. The use of reflection was also employed as part of this code logic. This code implementation imitates how the ASP.NET MVC framework uses attributes for field validation. I hope you've enjoyed this video on using attributes in C#. Please consider subscribing for more content on advanced C# topics and much more. And please ring the bell so that you'll be notified of future content. If you liked this video, please give it a thumbs up. It'll be greatly appreciated. Please feel free to share this video with anyone you feel may benefit from its content. I really enjoy reading your comments, so please feel free to engage with me in the comments section. As always, the code created for this video can be downloaded from GitHub. A link to the relevant GitHub repository is available below in the description. Thank you and take care.